Hi again, it's Alex here. So the next example we have for shaft design. So I will read it out. Now a steel shaft, part A, a steel shaft transmitting power shaft is 510 mm long and 50 mm external diameter. So the length here is given and the external diameter here is 50 millimeter. For part of its length, it is bored to a diameter of 25 mm and for the rest to 38 millimeter diameter. Now find the maximum power transmitted at a speed of 210 rpm if the shear stress is not to exceed. The maximum shear stress given here is 70 megapascal. And part B, if the angle of twist in the length of 25 mm board is equal to that in the length of 38 mm board, find the length bored to the later diameter. Okay, now here I have the diagram. So you have part A to part B here. That is the length of the shaft, which has the bore, that means the internal diameter of 25 mm. And then another section here, okay, that is a part of the shaft also, okay, which has an internal diameter of 38 mm. So the total length, let us take it as L, okay, and then we use a polar moment of inertia for hollow shaft. So that is pi d4 minus d4 over 32, the moment of inertia about the z-axis. So the shaft will be turning about the z-axis here. Okay, so part A, okay, now applying the principle of superposition. Now you have heard of what is principle of superposition. So and then also apply your right hand rules, okay, or either left hand rules. So this is the whole shaft with the length of L with a section of AB and BC. So what we need to do is we need to split it up into two sections based on AB and BC. So here you have AB and BC. So we have a torque of T, which is unknown yet. Okay, we have a torque of T on both the section. So based on the principle of superposition, since this section here you have no torque transmitted, nothing is given here at this section, so the resultant at section B should be actually equals to 0. So that is why when you look at this arrow is pointing towards the right and this arrow is pointing towards the left. So when you take T minus T, it will be equals to 0 here. So what we need to do is we split it up into section AB and make sure that it is in equilibrium. Okay, so when you put a T here at this side, at this end, so you must have a T here also as well, so that this equilibrium. So now since this is T, okay, and section B here is 0, so that is why I put a T here, so that the T minus T will be 0. This is right, pointing towards the right, and this is pointing towards the left. So for the equilibrium of this section BC, if I have an arrow pointing towards the right, then the other end should have the arrow pointing towards the left. So when you put T and the T here, okay, so you have this section here, C, is actually having a value of T, but the resultant of section B here would be 0, okay? Originally it's 0. Now, I have a statement here. For the shaft in series, usually, okay, if it is connected in this format or in this form, okay, we usually call it as a series bar. Now, so each part of the shaft is subjected to the same torque. So for any series bar or shaft, we usually consider that, okay, the torque transmitted to be equal, or it can be proven by based on the principle of superposition, that the torque at each section here, AB and BC, would be the same. So now, based on section AB with a diameter of 25 mm, we work out the polar moment of inertia for that section. So here you have 0.575 times 10 to the power of 6 millimeter to the power of 4, or if you convert this to meter power 4, then this should be 10 to the power of negative 6. So you have 0.575 times 10 power negative 6 if it is in meter power 4. So then for section BC, okay, we have the polar moment of inertia based on the internal diameter of 38 millimeter. We have the polar moment of inertia is 0.41 times 10 to the power of 6 mm to the power of 4. So we have worked out section AB and section BC. So for section AB again, based on the strength relationship, now what we are going to do is we are calculating the torque T here for the section AB. Okay, assuming the shear stress is at its maximum when the radius is maximum. I hope you remember, okay, based on the relationship of tau max over R max and tau min over R min, when R is max, the shear stress should be the maximum. Okay, so the external diameter, because the external radius or the external diameter of section AB and the external diameter or radius of section BC is the same. So based on this equation, I hope you remember, if this is R max, then you will have this as tau max. And since both the case we are referring to the tau max, then we are referring to the maximum radius here for both the section. Okay, so by putting in or by substituting in the torque, the radius, and this as the polar moment of inertia for section AB, so you have the torque as 805 Newton meter. But in this case, if we are calculating both section AB and section BC, okay, separately, then definitely we will get a different torque, because the polar moment of inertia for both the section is different, and it will be explained later which of the torque will be chosen as the common torque which is used to transmit power for the shaft. So the torque transmitted for section BC, now again, as you can see, both of these are the same amount of shear stress and the external diameter. The only thing different here is the polar moment of inertia. So you got the torque transmitted by section BC as 574 Newton meter. Now to the next slide. Now, since for the shaft in series, each part of the shaft is subjected to the same torque as mentioned, and also for both sections to transmit a common torque without failure, the minimum torque is chosen for safety purposes. So that means we will be choosing 574 Newton meter, actually, the common torque, that to be the common torque. Now, to prove that the torque transmitted is safe or not, therefore, you can see the working below here. So the shear stress, first thing is we calculate the shear stress. Now we assume that it is not 70. Okay, so 70 is a reference for us now. But the torque that we have adopted for both the section to be the same, common torque. So by putting in the torque, the polar moment of inertia, and the radius of section AB, you will calculate the shear stress. That means you will find the shear stress, found out that the shear stress for section AB is 49.9 megapascal, which is less than the given maximum shear stress at 70 megapascal. So that means the condition here for section AB by using torque 574 is safe. Okay, it's safe for the design. So and then proceed with section BC 574 common torque, because we are using common torque, and then we are recalculating the shear stress, okay, with a different polar moment of inertia. Then as you can see, section BC is actually taking up a shear stress of 70, which is equals to the 70 megapascal that is given by the question. So that means it is safe also. Okay. So now, then for the next one, okay, we are looking at the torque of 805 instead of 574 now. Why we are adopting 574 and not 805? Now you can see that the first condition is met, 70. Then the next one for section BC, okay, this is to be section BC, which has 0.41. Section BC, okay, so this is a section BC here, not AB. Section BC, this is AB here, and this is BC. Now you can see for BC, this should be changed to BC here, please. 98.2 megapascal is greater than 70. So it's a failure, okay, for the design of the shaft. So that is why we never adopt the value of 805, that means the maximum torque among both the cases. So that is why it is proven that 574 is safe and 805 is not safe to be considered as the common torque. Okay, so based on the common torque 574, then now we can calculate the power transmitted by the speed, substituting the speed and the torque. We got the safe power transmitted is 12.62 kilowatts. So that means the maximum power that can be transmitted by the shaft is 12.62 kilowatt. So that is for your section A. Now for section B, okay, based on stiffness relationship, okay, the part B is based on stiffness relationship, where they ask us to find out the length of the shaft. Okay, so you have this. Then TA and TBC, TAB and TBC is the same. The G is the same because the same material, so the shear modulus or the modulus of rigidity should be the same. The angle of twist is being adopted to be the same for both the cases. So based on this relationship here, T over G theta for both the case are the same. That means AB and BC are the same. So we only consider J over L here in this case. JAB over LAB should be equal to JBC over LBC, because TAB and GAB, theta AB is equals to T for the BC over G for the BC and theta for the BC. So that is why you have this relationship here. Okay, so manipulating, so you got the length ratio to the polar moment of inertia ratio. So putting in the JBC and the JAB, so you've got to know that LBC over LAB is 0.71304. Then with this, substitute the 0.71304 LBC for the LAB. So you have this equation, and we will be able to find out the length of the BC. So it's 297 millimeter. And once you got LBC, then you will be able to find the LAB by taking 297 multiplied by 0.71304. So you have LAB is 213 millimeter, whereas LBC is 297 millimeter. Thank you very much. That's the end of this slide, okay, or podcast. Please, if you have any questions or comment, please put on the comment section in my YouTube for shaft design. Thank you very much. See you again soon. Bye.